Example on step-down DC to DC converter. In the previous video, we have presented the basic theory of step-down DC to DC converter, and we said that it is composed of a choppering circuit that choppers the input DC voltage such that the output here will be equal the input at the switch is on, and it would be 0 when the switch is off. And by taking the average, we can control the output DC voltage at the load. Now, let us discuss a numerical example for such simple step-down DC to DC converter. We say that the DC converter in the figure has a resistive load R equals 10 ohms. So the value of R is 10 ohms. And the input voltage Vs is 220 volts. This is DC volt. When the converter switch remains on, its voltage drop is V chopper is 2 volts. Here, it is not assumed that the switch is idle switch. No, it is assumed it is a practical switch and there is a voltage drop on the switch. So when it is on, there is a voltage drop at the switch equals 2 volts. This means that if I have the source voltage 220 volts and I have voltage drop 2 volts here, the volt that actually reach to the load is 220 minus 2 volts. So it would be 218 volts. So when the switch is on, there is a voltage drop at the switch 2 volts. In our discussion of the DC to step-down DC to DC converter in the previous video, we didn't assume that there is a voltage drop on the switch. We assume that idle switch. And the choppering frequency F equals 1 kilohertz. This means that there is a choppering frequency, or in other words, 1 over capital T equals 1 kilohertz. If the duty cycle is 50%, this duty cycle is a small k. Determine what is the average output voltage VA, what is the average voltage at the load, what is the root mean square output voltage Vout, VO, what is the converter efficiency. If we remember the parameters of the converters, we will see what is meant by the converter efficiency. What is the effective input resistance? As we have seen in the previous video, the input resistance at the source is R over K. So this is another point. What is the input resistance or input of the converter? What is the rebel factor of the output voltage? Rebel factor of output voltage. What is the root mean square value of the fundamental component of the output harmonic voltage? Here we are talking about the harmonics, so we are going to see the harmonics too. Let us go step by step. The first one is the average output voltage. As we said before, the average output voltage is K multiplied by Vs. But now it is not completely Vs, it is Vs minus V chopper or V switch. So we have Vs equal 220 volts. The duty cycle is 50%, K equals 0.5. The load resistance is 10 ohms, and the choppering voltage or the voltage on the switch is 2 volts. So the average voltage, we know that is K multiplied by Vs, but now we are talking Vs minus the chopping. So K 0.5 multiplied by Vs minus V chopper. Vs minus V chopper. So the average DC voltage, it would be 109 volts. If the chopping voltage was 0, it would be 110 volts. Alright, because it would be 0.5 multiplied by 220 divided. The root mean square output voltage, V output, we proved that is the square root of K multiplied by Vs. Once again, we are going to replace Vs by Vs minus V chopper. So, it would be square root K, square root 0.5, multiplied by 220 minus 2. It would be 154.15 volts. What is the output power? The output power would be the integration from 0 to kT V out squared over R dt multiplied by 1 over T. Alright? According to this, it would be 1 over T. The output voltage squared is V source minus V chopper, because once again, the voltage that appears on the load is V source minus V chopper. V source minus V chopper squared over R dt. By taking this integration, it would be kT multiplied by V source minus V chopper squared over R multiplied by 1 over T. So it would be K V source minus V chopper squared over R. K is 0.5, V source is 220, V chopper is 2, and R is 10. By taking these values, we can calculate the output power as 2376.2 watts. Right? This is the output power. The input power, on the other hand, is 1 over T, the integration from 0 to kT. If I'm talking about the input power, I'm talking from here. So from here, this is Vs multiplied by I. This is the input power. I'm not talking about what is the shopping here. I'm talking about the input power. So the input power is 1 over T, the integration from 0 to kT, Vs multiplied by I dt. Vs is Vs. What is I? I, the current passing here, is Vs minus V chopper over R. So Vs multiplied by I is Vs minus V chopper over R. And the limits of integration from 0 to kT, and it would be multiplied by 1 over T. By developing this integration, it would be kT multiplied by Vs multiplied by Vs minus V chopper over R multiplied by 1 over T. 1 over T would be eliminated with T, so this would be K multiplied by Vs multiplied by Vs minus V chopper over R. K is 0.5, Vs is 220, Vs minus chopper is 220 minus 2 over R over 10. By calculating this, we find the input power is 2398 watt. Now we have the output power and the input power. From the output power and input power, we can calculate the converter efficiency. The converter efficiency is the output power over the input power. So it would be 2376.2 over 2398. It would be 99.09%. It should be noted that this is the converter efficiency. The converter efficiency relates the output power at the load to the input power at the converter. But this is not the conversion efficiency. If we are talking about the conversion efficiency, we are talking about the DC power, BDC over B root mean square. Or okay. The effective input resistance R input is the V source over the current IA, or the average current. The average current is V average over the resistance R. It should be noted here, it is not so simple as was before. It is not R over K, because we have the choppering voltage here. So in this case, we are talking about the input source voltage over the DC output current in the resistance. So V source over the average DC current to be V average over R, and already we calculated V average as 109 volts. So 109 over R over 10. So we can find that the equivalent input resistance is 20.18 ohms, right? 20.18 ohms. This is the effective input resistance. The output ripple factor would be V ripple over the average voltage. The V ripple is obtained as the square root of the root mean square voltage square minus the V average square. And already we calculated the root mean square voltage as 154.15, and we calculated the average voltage as 190 volts. From this we can obtain the ripple voltage. Now V average is K multiplied by V source, and V out is the square root of K V source. So we can replace this V output by square root K V source, and replace this V average by K V source. So this would be K V source square minus K squared V source square. Alright, this is the ripple voltage over V average, which is K V source. By arranging these pieces together, we can prove that the ripple factor at the output, V ripple over V average, V ripple this quantity and taking in consideration this V naught and VA, over V average, taking in consideration V average is this, we can prove that V ripple over V average is the square root of 1 over K minus 1. Now we have K is 0.5, so the output ripple factor is the square root of 1 over 0.5 minus 1, and according to this 100%. Actually, this can be done by what we have already calculated for V output and V average, these values, V out and V average. And from this V out and V average, we can calculate V ripple, and from V ripple divided by V average, we can calculate the ripple factor without the need to prove this rule. Okay. In any case, this is a simple proof. You can do it by yourself, or you can use the values dial. In both cases, you will find that the ripple factor at the output is 100%. On the other hand, it is required to find the first harmonic voltage. So to obtain the first harmonic voltage, we look at the output voltage. We can find it as a rectangle pulse function, which can be represented in terms of a Fourier series as a DC component or average component plus series of uh, cosine 2n by ft with amplitudes and plus series of sine 2n by ft with its amplitudes from n equals 1 to infinity. For n equals 1, this is called the first harmonic. So the first harmonic or the fundamental harmonic or fundamental component for n equals 1 of the output voltage is obtained by setting n equals 1. So the first harmonic V1 of t, it would be the value of the source minus the choppering, because we are going to replace any Vs here by Vs minus V chopper over n by, we are talking about n equals 1, so n1 multiplied by pi multiplied by sine 2 by k cosine 2 by ft. This is the first term based on the cosine plus 1 minus cosine 2 by k sine 2 by ft. From this, we can arrange the sinusoidal forms or the harmonic forms, the first harmonic form, in terms of a sinusoidal form only. So it would be 220 minus 2 over pi multiplied by 2 multiplied by sine 2 by 2 by f, where f is 1 kilohertz t. So we are talking about this term only. Actually, I think that the value of k is 0.5. So 2 pi multiplied by 0.5, it means that pi. Sine pi is 0, so this term is 0. Now 2 pi multiplied by 0.5 is pi. Cosine pi is minus 1. Minus 1 minus minus would be plus 1. 1 plus 1 is 2. So this is 2 sine 2 by ft. This is the fundamental harmonic component or the first harmonic component. By taking its amplitude, we can find that the amplitude of the first harmonic is 138.78 sine 2 by ft. Now the amplitude or the magnitude here is the V maximum. If we are talking about the root mean square of the first harmonic, it would be V maximum over square root 2. As we know, the root mean square of any sinusoidal is the maximum value over square root 2. So the root mean square value of the first harmonic is 98.13 volts. By this, we have completed all the requirements: the average output voltage, the root mean square voltage, the converter efficiency, the effective input resistance, the rebel factor of the output voltage, and finally, the root mean square voltage of the fundamental component. Okay? Alright.